Now I will introduce this paper named Stick-Slip Vibration Behaviors or BHA and its control method in highly deviated wells. Stick-slip vibration is a common phenomenon met in oil gas drilling, especially in the complex trajectory wells such as highly deviated wells. It will cause the earlier failure of BHA and lower drilling efficiency. In this present paper, a finite element model of highly deviated well, which consists of a drill string system, a borehole, a PDC bit, and a rock model, is carried out to investigate the stick-slip vibration behaviors of drill bit and BHA. Besides, the torsional impact drilling method is proposed in the context to control the stick-slip vibration of BHA. Nowadays, the highly deviated drilling approach is widely used in oil gas drilling. It breaks the limitation of drilling space, especially in offshore and beach oil exploration. It has the merits of low drilling costs, high economic benefit. The so-called highly deviated well is the directional well of which the ratio of well length is vertical well depth larger than 2 and the deviated angle is ranging from 55 degrees to 85 degrees. However, there is a special engineering phenomenon in the highly deviated well drilling process. It is called stick-slip vibration. That is, the drill bit stops rotation due to the torque which transmitted from the rotary table through drilling string is not enough to break the bottom hole rock in a certain period of time. Subsequently, with the rotary table keeps rotating and the torque keeps transmitting to the drill bit abrupt rotates when the energy stored in drilling string is enough to break the rock. Stick-slip vibration of drill string is bit stalling and rotate continuously alternating cycle. The bit when sudden rotation speed and acceleration are usually higher. It leads to the drill bit and BHA fail early, and cause the low quality of well borehole. It is therefore significant to investigate the stick-slip vibration control approaches for improving the ROP and reducing the drilling costs. This paper adopts the real-time rock breaking simulation to mimic the bottom boundary condition of nonlinear dynamic model of drilling string system in highly deviated well. In this model, contact between drilling string and the wellbore wall, drill bit and rock are successfully addressed. The schematic diagram of simulation model, which includes drilling string, borehole, drill bit, and rock is plotted, just shown in Figure 1. Taking the N12X168 well in Jingdong oil field of China as an example, its spatial trajectory is plotted in Figure 2. By comparing with the field mirror data, it can be concluded that the dynamic bend element model of highly deviated well established in this paper has certain accuracy and rationality, which can reasonably reflect the dynamic characteristics of drill string in the actual drilling process of high deviated well. Figure 4 presents the rotation speed vibration of drill bit with respect to simulation time. It can be seen that the phenomenon of stick-slip vibration is extremely obvious. The drill bit presents a reduplicative stick-slip state during the drilling process. When the rotation speed of drill bit equals to or less than 0, it means the drill bit is in the slip state. During the slip state, the PDC cutter will suffer violent impact loading because of the high rotational speed of drill bit. This will cause the earlier failure of cutters. Meanwhile, the torque is keeping transmitting to drill bit from rotary table, and the energy is stored in the drilling string before the next slip state happens. If this energy stored in the drilling string is large enough to let the drill bit escapes from the stick state, then the slip state occurs. The absolute angular displacement of rotary table is increasing linearly with the time. In contrast, the absolute angular displacement of drill bit presents a stairs type to rise continuously. The rotation of drill bit has certain hysteresis with respect to the rotary table. The drill bit has rotation speed until at point A, just as Figure 5 shows. Before reaching point A, the rotation energy transmitted from rotary table is stored in drilling string system. Subsequently, the drill bit obtained a high rotation speed, resulting in angular displacement sharply reached point B. During the gap between point B and C, the angular displacement of bit almost keeps constant. It means the drill bit is stopping rotation and waiting for the next cycle of stick slip. The drilling string has small deformation at the beginning rotation and a large deformation will take place in the subsequent rotation. It almost presents a helical buckling deformation due to the torque transmitted from top to bottom of the drill string. A large part of the energy which causes stick-slip vibration or BHA is stored in the drilling string system, and this energy is the main reason for the drilling string deformation. When the drill bit is in steady state and without rotation, the energy stored in the drilling string system is increasing and the drilling string deformation becomes more obviously. In contrast, when the stored energy released in the sleep state, the drilling string deformation will be reset. Figure 7 shows the lateral acceleration variation of drill bits with respect to simulation time, including two directions, x direction and y direction. The vibration of BHA is very complex. The different types of vibration mixed together, such as lateral vibration, axial vibration, torsional vibration, and whirling motion. Generally, the vibration of BHA is extremely intensive. It has a great influence on the BHA working life and the whalebone stability. Figure 9 shows that the maximum lateral vibration is nearly 30 G. The intensity of lateral vibration is related to stick-slip vibration. When the drill bit is in steady state, the lateral vibration of BHA is weak. On the contrary, if the drill bit is in sleep state, the lateral vibration presents extremely intensive. Figure 8 plots the penetration depth of drill bit with respect to simulation time. The penetration depth presents a stairs type to rise continuously, just like the curve of absolute angular displacement of drill bit in Figure 7. In stick state, the penetration depth is hard to increase and almost keeps to a constant. However, the penetration depth sharply increases in sleep state of drill bit. That is, means the stick state of drill bit has no contribution to rock breaking process and will decrease the drilling efficiency. Hence, the effective drilling time should be increased by reducing the period of bit sticking in the actual drilling process. Figure 9 presents the drilled bottom-hole rock at 6 different moments. The drill bit will rotate and cut bottom-hole rock while the torque and W will be transmitted to drill bit, causing a grooving formed. With the drill bit keep breaking the rock, the breaking pit is gradually formed and more obvious. Figure 10 represents the rotation speed vibration of BHA at different distances. 60 meters, 200 meters, 400 meters, and 800 meters from the drill bit. The stick-slip vibration at the distance of 30 meters from drill bit is more obvious than the distance of 800, and there is no stick-slip vibration happening at the rotary table. It therefore can be concluded that the phenomenon of stick-slip vibration of BHA gradually weakened and disappeared with the distance from the drill bit increases, and stick-slip vibration mainly occurs at the BHA which near drill bit. Figure 11 shows the missile stress and flexural motor nephogram of BHA. The missile stress nephogram illustrates the top drilling string suffers tensile load and BHA suffers compressive load. The flexural moment nephogram presents that the maximum flexural moment occurs at the BHA which near the drill bit. It also means the BHA is prone to fracture. Figure 12 illustrates the rotation speed vibration of drill bit in torsional impact drilling and traditional drilling with respect to simulation time. The stick sleeve vibration is weakened in torsional impact drilling comparing to the traditional drilling. The maximum rotation speed in torsional impact drilling is 262.2 rpm and it is 350 rpm. In traditional drilling, a reduction of about 25.09%. Hence, it can be inferred that the high-frequency torsional impact drilling method can reduce the stick slip vibration and lead to the BHA more stable during drilling process. Figure 13 shows the angular displacement variation of drill bit in torsional impact drilling and traditional drilling. Comparing the angular displacement curve of traditional drilling, the angular displacement curve of torsional impact drilling presents more smooth. The stairs type to continuously rise is not obvious. It also indicates that the torsional impact drilling can reduce the stick slip vibration and lead the BHA more stable during drilling process. Figure 14 presents the resistance torque of drill bits in torsional impact drilling traditional drill. The resistance torque of drill bit is reduced obviously in torsional impact drilling comparing to the traditional drilling. The maximum resistance torque is reduced from 27.8 kN to 17.4 kN while using torsional impact drilling method. It presents a reduction of approximately 34.71% compared to conventional drilling. It indicates that torsional impact drilling method can reduce the resistance torque of drill bit and make the rotation of drill bit become relatively more stable. The resistance torque of drill bit is mainly source of stick slip vibration. Reducing the torque amplitude and fluctuation can obviously eliminate the stick slip vibration in drilling process. Figure 15 shows the comparison of penetration depths of drill bits in torsional impact drilling and traditional drill. In torsional impact drilling, the penetration depth curve presents a linear growth with respect to simulation time. It is different from the stairs type of continuously rising in traditional drilling. It also can be seen from the figure that the rate of penetration in torsional drilling is larger than it in traditional drilling. Torsional impact drilling is increased the drilling depth by about 58.28% compared to traditional drilling. This means the torsional impact can effectively improve drilling efficiency. The research results show that the phenomenon of stick slip vibration of BHA gradually weaken and disappear with the distance from the drill bit increases, and the stick slip vibration mainly occurs at the BHA which near drill bit. The high-frequency torsional impact drilling method can reduce the resistance torque of the bit by 34.71% and increase the drilling depth by about 58.28%. It can effectively improve the drilling efficiency of the bit, making the rotation of drill bit becomes relatively more stable, and reducing or even eliminating the stick slip vibration. These results lead to an enhanced understanding of stick slip vibration behaviors of drill bit and BHA in highly deviated wells and provide the basis for improving the drilling efficiency. This is all the introduction of this paper. Thank you for your listening.